Good afternoon. This is Patricia Balderas. Verónica Nieves Cruz and I, we will present the following paper, Estimation of Travel Time for Additional Metrobus Route.
We present some results of the research with application case study format of a simulation model. The simulation model was developed with Maple tools. The main objective was to estimate the travel time for the proposed extension on the Metrobus line, considering the travel time between two adjacent stations, the waiting time at each station, and the waiting time and intersection with traffic lights. The agenda for this presentation is Introduction to the Study Context, the Connection Proposal, the Simulation Model, Result Discussion, and Conclusions.
Urban mobility is closely related to the daily movement that people need to carry out to achieve comprehensive development involving the movement of people and goods from one place to another. Currently, most people use public transport system as the main option for transportation. So, the growth and urbanization of many regions demand accessible and efficient public transport systems that allow their comprehensive development. However, there are several factors that impede suitable operation of public transport units, harming urban mobility. Some of these factors are existing imbalance between user demand and available offer, lack of adequate infrastructure for the operation of public transport units, interaction of public transport units with private vehicles of independent travelers, which many times cause areas of vehicular congestion. Simulation models also offer high flexibility to represent systems of different types and allow to propose improvements and solutions to problems of the real system. Where mathematical model formulation with complex analytic expression impedes finding solutions due to the complexity to solve them, and even sometimes it is difficult or impossible to solve them. This work corresponds to the development of a computational simulation model. Therefore, the simulation model concept is used to refer to a computational simulation model. Regarding the implementation method, Robinson 2014 classified the simulation models into four categories. Discrete event simulation. This method simulates the interaction of entities in discrete systems. The main objective is to track in detail the movement of entities, people, objects, or information through the system. Monte Carlo simulation. In this method, random variables are generated and they interact with each other to generate results to support the analysis and prediction of the behavior of some variables of interest. Dynamic system simulation, it is used a continuous approach over time. It refers to flows of objects, people, vehicles, money, matter. These flows simultaneously integrate and disintegrate the blocks that make up the system. The size of these blocks keeps changing constantly depending on the flow that enters and leaves them. Agent-based simulation. With this simulation method, the objective is to model and analyze the community behavior of a population agents where each agent has characteristics and behaviors, but community behaviors emerge from the joint interaction. Due to the importance of urban mobility, the proper operation of transport system, and the consequences that their operation can generate, this paper addresses a proposal for connecting three stations of two transport systems in Mexico City: the Mexico City Subway System, MCSS, and the Metrobus System, MS. We estimate the travel duration of the two proposed routes made by Metrobus units located in Coyoacán. Then we compare the results with the duration of trips that are currently made by buses, minibuses, and vans. This proposal was developed after a long period of observation and data collection within the region involved. The proposal arises in response to the observation and analysis of the current situation, in which PTU routes could generate congestion points due to the inadequate existing infrastructure on streets, continuous bus stops, the circulation of a large number of PTU, and the long duration of trips, aspects that harm urban mobility in the area. See Nieves 2020 for more details. The proposed connection as an extension of the MS line has an origin and destination points on the two existing stations. Once the first route connects the MS line to the MCSS station, the second route allows the connection in the opposite direction. In this way, after completing both routes, the MS units return to the same MS line. The proposed routes are from point A to point B and from point B to point C, where A and C are adjacent stations on a MSA line and B is a terminal station on an MCSS line. Several aspects were considered as the existing infrastructure of streets and avenues, traffic light signals, and the direction of current vehicular flow. The infrastructure and existing traffic law around the Station A prevent a direct connection between B and C. For this reason, Station C was considered. This proposal offered one more point of connection between the lines and between both systems, but in the southern area, which could be quite beneficial for workers, students, and general users whose point of origin or destination are there.
Now I'm going to talk about the model. First, I want to explain the picture above in this slide. This is a graphical representation of the proposed routes. Remember that A and C are stations of the Metrobus system, and B is a terminal station in subway system. First route is from point A to point B, and second route is from point B to point C. Both proposed routes consider two intermediate stations, S1 and S2, and they also consider three traffic lights. They are TL1, TL2, and TLT. These elements of the routes define some sections into them. For example, S1 and S2 define 3 sections, and 3 traffic lights define 4 sections. In this case, we have many sections, but some of them are very short. For example, the section between Station A and the traffic light TL3, or other example is the section between the station S1 and the traffic light TL2. As a simplification in this model, we only consider the biggest section. These are shown in the below picture. Here we have 3 sections into first route and 4 sections into second route. After that, the total duration T of each route considers 3 important variables. They are T subscript T, it is the travel time between 2 consecutive stations or between 1 station and 1 traffic light. T subscript S, it is stop time in bus stops. And T subscript TL, it is traffic light time. Then T is the addition of these 3 variables, T subscript T plus T subscript S plus T subscript TL. There are some general assumptions for this model. First one, both routes consider 2 intermediate stations and 2 traffic lights. These elements were shown in previous slide. Second assumption is related to stop time. This variable is modeled by beta distribution. First 2 parameters are form parameters. Then there are the minimum value in 8.13 and maximum value in 13.35 seconds. It's important to say that these parameters correspond to the feed data that we collect as a part of a more extensive investigation of this proposal. For that, we consider 5 stations on the Metrobus system line. Station A, Station C, 2 more stations before A, and 1 more after Station C. For this assumption, we have traffic light depends on the total duration of the traffic light cycle and the duration of the green light. For example, on the right, there are the parameters of the traffic light TL3. The first parameter is TL, total light, equal to 100 seconds. The second parameter is YL, equal to 25 seconds. This is the parameter of the green light. The green line refers to the time in which one unit of the Metrobus can continue its movement. So, if the traffic light is not in green light, the Metrobus unit needs to stop and wait. In green light, Metrobus units don't need to wait, but in other case they need to wait between 0 and 100 minutes 25 seconds. That's to say, they need to wait between 0 and 75 seconds. With these two parameters, TL and GL, traffic light times are calculated. Finally, fourth assumption is about travel time. This variable is modeled by normal, log normal, and Weibull distribution. They are also defined from the feed data of collected information. They model the average operation speed of the current Metrobus units in the light. Speed parameter is in meters per second. To get the travel time, first the average speed into each section is calculated. After that, we consider the length section and use this expression for the travel time. Now, why we consider tree distribution for the travel time? It is because the average operation speeds depend on the longest subsection with a traffic light or intermediate station, where Metrobus units operate without stopping. This is applied in each section according to the table on the right. Weibull distribution is used for short subsections. Normal distribution is used for minimum length subsections. And finally, log normal distribution is associated with the longest subsections. Here, I'm going to present the general structure of the model as a Maple worksheet. The picture in the right shows the general structure of the model. At the beginning, there are some packages and specific tools that we use in this model. After that, there is the input parameter section. There are three kinds of parameters. General parameters, they are route specifications. Probability function parameters, which define operation speed and time in station. Finally, we have parameter for result analysis. The use of random variables in simulation model is an important property. Because of its use, it is possible to get different values of the output variables in different execution of the model. For this reason, it's not appropriate to formulate a conclusion from only one execution. Instead of to analyze the behavior of a set of replicas, it's better to give a conclusion. We consider one data D as the total travel time for one specific route and one replica R as a set of the data. Then, for result analysis, we need to define these two parameters. After that, we have a set of auxiliary functions. First, we have traffic light vector, section travel time vector, and stop time vector. They are related with the variables T subscript TL, T subscript T, and T subscript S, but they not only calculate one value, they calculate the values and save them in a row vector. After this function, we have route evaluation function. It adds the value of three previous components and converts the results to minutes. It is because previous functions use seconds as time unit, but results were present in minutes in order to give a perceptible quantity. For this function, it is necessary to specify a route, its section, and indicate if there are intermediate station and traffic lights. Later, we have the matrix evaluation. It uses previous function and repeats the process R times. It stores the data as a matrix with R rows and D columns. The last auxiliary function is confidence interval. It calculates the confidence interval to the sample of random variables, in this case the mean of each replica. Finally, as other section, there is the model. It uses all the previous functions and shows the result in a graph. In this slide, we present the structure of the model section. Here we use the auxiliary function and create the graph to present results. This example is for first route, from point A to point B. The graph shows three important values from each replica: minimum value in red color, maximum value in blue color, and average value in black color. With this graph, we can see and analyze the behavior of these three variables in each replica. We also get the global mean from all data and the confidence interval for the mean. The global mean is shown as a horizontal green line in the graph. In this execution, the global mean is 6.4 minutes, and the 95% confidence interval is defined by 6.39 and 6.42. That means travel time is around 6.4 minutes, and intuitively, the confidence interval of the mean indicates that if we execute the model 100 times, 95% of the times, the mean value in each replica will be between 6.39 and 6.42 minutes. From the graph, we can see that average values are more stable than minimum and maximum values, because latter present large oscillation. What happens if we modify the parameter d? As an experimental process, it is found that for small values of d, the corresponding graph on the average values presents greater oscillation around the global mean. On the other hand, for large values of d, these oscillations are minimal. For example, for r equal to 100 and d equal to 20, there is the graph on the left. We can see greater oscillation in the average graph compared with the graph on the right. In this graph, d is equal to 1000. In this case, the average graph appears almost as a straight line. Hence, in replicas with a greater number of data d, more stable results are obtained. In this slide, we present the results for both proposed routes. We use r equal to 100 and d equal to 102. On the left, we have the result for first route, from point A to point B. The total mean is around 6.4 minutes. For second route, the global mean is around 8.88 minutes. These results are compared to current travel time by buses, minibuses, and vans in next slide. This graph compares the travel time by buses, van, and Metrobus units. We defined travel T1 as the route from the Metrobus system to the subway system, and travel T2 as the route from station B to one station of the Metrobus system. The travel time for proposed routes are present in gray color. These have the shortest time in both travel, T1 and T2. Then, it is estimated that in both proposed routes by Metrobus units, the travel time is shorter than in the current routes by buses and vans.
Here are some conclusions. First one is we present a proposal for connecting between two transport systems in Mexico City, and it was analyzed with a Monte Carlo simulation model. The proposed routes are favorable in terms of travel time. The simulation model and the analysis of results through replicas allow to visualize several scenarios. This proposal is studied in more detail and from different perspectives in a broader investigation of Nieves 2020. Maple was a very useful programming language to develop simulation models for this study and has packages and functions that easily help to structure these models. Finally, here are some reference and bibliography. Then, we say thank you for all of you to pay attention to this presentation.